Hey everyone, I'm Amriza Burakawan and welcome to Algorithm Academy. Today, we are tackling a well-known and fundamental problem, RMQ or Range Minimum Query. But don't click away just yet. This video will take a fresh approach compared to typical RMQ tutorials. The problem name describes the problem. We are given an array and we'll face multiple queries in form of L and R, where we need to find the minimum element in that range, like you can see on this slide. There is a straightforward method to solve this. When you see this problem at the first time, you have some very easy code to implement that in O1 ON time complexity. It means O1 for pre-processing and ON for processing each query. We simply loop over all elements in the range to find the minimum. And also in this code, you can use min element in C++ to just easily answer all of the queries. Here we have another naive approach with ON to the power of 2 pre-process and O1 per query. The trick behind this solution is we cache or pre-process all of the possible queries that we can face. And then when we receive a query, we simply just print the answer and that's it. And now let's aim for something better. How can we optimize this? Try to divide the running time by a constant factor like 2, 5, 10, something like that. Start with these values. Take a moment to pause the video and think about it. Give yourself at least 15 minutes. I think you found the idea. Our approach is to divide the array into blocks, let's say blocks of size 4, and pre-process the minimum for each block. This reduces the time for query by a factor of 4. Here is an example. We want to find the minimum of a range in the array. So the query starts here and ends here. We want to find the minimum of all elements in this range. We first start with a single element. Here, A3, which is 2. And then we speed up using the blocks, the pre-calculated values like this one, B1 and B2. Here is the array B, the blocks, the minimum of blocks, and then B1 and then B2. And here we have again 2 single elements to process, 4 and 2, and we calculate minimum of all of this, A3, B1, B2, A12 and A13, and the minimum is 2. And instead of calculating 11 elements, minimum of 11 elements, we just calculated minimum of 5 elements, just 5 operations. Now you might wonder, why stop at 4? Why not 10, 20 or even more? The challenge lies in finding the optimal block size. If the blocks are too large, the number of single elements we have to process grows. It's a trade-off. What is the optimal choice? Optimal choice is a square root. So we use a square root decomposition here. This structure handles updates efficiently too. So if you need to update an element, we can do that without much hassle. We'll dive into even faster solutions and more advanced techniques going beyond RMQ in the next parts, so stay tuned. Okay, now let's solve the problem RMQSQ on SPOJ using what we learned, and I put the link to this problem on the description. So the problem is simple, is what we talked about. It gives us an array and Q queries and asks for minimum element in each range. So first of all, we start with getting the input like this. I already did that. So then we define something as a square root. Let's fix it at 300. And then we start by calculating minimum for each block. So it's like this. So it calculates the minimum in this range, and then we start getting the queries like this. I'm gonna show you a very short method of implementing Sqrt decomposition. You can use it in other problems too, not just this problem. So I start with very big ants, and then I'm gonna move L one by one to the right, and in some cases I'm going to jump. So when I can jump if L is the start of a block, and also if I jump I don't go after R. So it's like while L is less than R, then I try to jump. So for jumping, if L is divisible by S, which is size of block, and also L plus S doesn't go over R, I can use answer for this block, which is BL divided by S, and else I process this single element like this. So in this case I need to jump like this, and now I print the answer. So let's test and make sure this code works, and then we can submit. Okay. In this problem everything is zero based, so what I did here is wrong. So we need to add 1 to R. So I consider that like problems on code forces it's zero based, but it's not. And okay, now the answer matches. Let's submit. Okay, we solved this problem, and here was solving RMQ using Sqrt Decomposition.